Hi. Our optimization techniques and our graphing techniques rely on the fact that if f prime is positive in an interval, then f is increasing there. And if f prime is negative on an interval, then f is decreasing there. The basis for this result is the mean value theorem. This video comes after the video on Rolle's theorem, which is the basis for the mean value theorem, or MVT, which goes like this. Suppose f is continuous on the closed interval ab and differentiable on the open interval ab. Sounds familiar? This is almost the condition of Rolle's theorem. The only thing missing is that f of a is equal to f of b, a requirement for Rolle's theorem, which is not needed for the mean value theorem. In other words, the point on the graph corresponding to A and the point on the graph corresponding to B, now they don't have to be at the same level. The y coordinates, they can be the same, but the thing is, they don't have to be. It's not needed by the mean value theorem. Well, okay then, what's the conclusion? Just like Rolle's theorem, the MVT is also an existence theorem. The conclusion is that then there is some number c in the in the open interval AB, such that f prime of c is equal to f of b minus f of a divided by b minus a. The conclusion of Rolle's theorem involves f prime of c being equal to 0 for some number c. Now, where did this fraction come from? We'll explain the geometric significance because, well, if you consider the graph here, you have the endpoints at A and B not being horizontally aligned because the y coordinates don't have to be the same, meaning the slope of this line connecting them isn't 0. What then is their slope? Well, the slope is the difference of the y coordinates. That's going to be f of b minus f of a, the numerator of this fraction. And what about the denominator of the slope? It's going to be b minus a. So in other words, this fraction I'm encircling here is the slope of this line connecting the endpoints. In other words, what we're guaranteeing in the mean value theorem is that there is a number c such that f prime of c, the slope of the tangent line, is equal to the slope of the secant line connecting the points at A and B. As you can see in the illustration, there are 2 points here because the point C is not unique. So in this illustration, there is a location C1 and a location C2 x coordinates where the corresponding tangent lines are parallel to the secant line connecting the points at A and B. So that's the geometric significance. And then interestingly, if we do happen to have f of a equal to f of b, what's going to happen to the fraction on the other side of f prime of c is that it's going to be 0, meaning this reduces to the conclusion of Rolle's theorem. In other words, Rolle's theorem is a special case of MVT, or equivalently, MVT is the more general statement of Rolle's theorem. Why is the mean value theorem true? Alright, before we jump into the proof, one of the things that we're going to need is the slope, or not just the slope, but rather the equation of the secant line at the endpoints A and B, which is given in a straightforward fashion by this equation. So here you have the slope f of b minus f of a over b minus a, and then let me use the coordinates of the point at A, so that's the reason for x minus a here, and on the other side, y minus f of a. Don't forget that's the equation of the secant line. To prove the mean value theorem, let me define this new function small g. G of x is equal to f of x minus this particular expression, which if I point out that it's the y representing the secant line, then now it doesn't seem like something pulled out of thin air. Alright, and then why the function g has to be defined this way is going to be justified by the proof. Just like the proof of Rolle's theorem, sit back, relax, and enjoy, and come along for the ride. Alright, so what we're going to do with the function g is we're going to verify it satisfies the conditions of Rolle's theorem and essentially applies Rolle's theorem on the function g. Alright, so, is the function g continuous? Well, it's the difference of two continuous functions. F is continuous as given, and then the thing inside the brackets. Note that that's a linear function, therefore it's continuous. It's a polynomial. So therefore the difference g is continuous. Is the difference g differentiable on the open interval ab? Well, the function f, as given, is differentiable on ab, and then the secant line, this linear function being a polynomial function, is of course differentiable everywhere, and therefore also in ab. So therefore, the function g is continuous on the closed interval ab and differentiable on the open interval ab. But I said we want to apply Rolle's theorem on G, so we have to verify it satisfies the very last condition. Is G evaluated at A and then at B going to give us the same values? Well, let's plug in A into G, G of A. So what's going to happen here inside the brackets, you're going to have this zeroing out, leaving us with just f of A. But then outside the first term is f of A. Take the difference, you get 0. Now what about G of B? When you plug in b here, this b minus a will cancel with the denominator, leaving us just the numerator. But when you add f of a to that, we're left with f of b inside the brackets. And then if x is to be replaced by b, so this would also be f of b, the result is going to be 0. So meaning the function values of g at a and b are going to be equal because they are both 0. Now, Rolle's theorem couldn't have been applied to the function f because f of a did not have to be the same as f of b. But we're sure g of a is equal to g of b. The conditions of Rolle's theorem are all satisfied by the function g, and therefore we get the following conclusion. There is therefore some number c inside the open interval ab such that g prime of c is equal to 0. Now let's go back to the original definition of g as this particular difference. Well, then how does its derivative look like? Well, then we take the derivative of the two things being subtracted. G prime of x is equal to f prime of x minus the derivative of this linear function. But hey, because that's a linear function, isn't its derivative just going to be its slope? This f of b minus f of a over b minus a thing. Alright? So if we plug in c in place of x here, then you're going to get on the right side f prime of c minus f of b minus f of a over b minus a. But hey, did we just say g prime of c is 0? Then if you rewrite this equation, we're going to end up with the conclusion of the mean value theorem. F prime of c is equal to f of b minus f of a over b minus a. The mean value theorem is correct. Yay! Now we're going to use this to prove some theorems and exercises. For reference, here is a statement of the mean value theorem. Alright. Example. Two stationary patrol cars equipped with radar are 5 miles apart on a highway. Let's assume it's a straight highway. As a truck passes the first patrol car, its speed is clocked at 55 miles per hour. And then 4 minutes later, which is 1/15 of an hour for easy reference, when the truck passes the second patrol car, its speed is clocked at 15 miles per hour. So you have a car moving along a straight highway, two patrol cars, 5 miles apart. The first patrol car detects 55 miles per hour. The second patrol car detects 15 miles per hour. Prove that the truck must have exceeded the speed limit of 60 miles per hour at some time during the 4 minutes. Alright, now this problem is asking us to prove something about the speed of the car. Well, the speed is a scalar version of the velocity, and the velocity, remember, that's the derivative of the position function. So we're going to start things off with trying to represent the position function. Let's use s of t. The position of the truck on the highway, assuming that you have positioned a number line, and for specificity, s of t is measured in miles from the first patrol car, t hours after passing the first patrol car. So imagine when the truck passes the first patrol car, that's at time 0 and position 0. And then when our truck passes the second patrol car, that's, well, the position, s t hours after. All right, so assume S is continuous on 0 to 1 over 15. 1 over 15, as pointed out above, is the duration of 4 minutes. So why this interval? Because the time horizon is those 4 minutes. Oops, I made a typo here. This should be an open interval. So assume S is continuous on the closed interval 0 to 1 over 15 and differentiable on the open interval. That's supposed to be open from 0 to 1 over 15. According to the mean value theorem, because the conditions are satisfied, there should then be some number c inside the open interval 0 to 1 over 15 such that S prime of c is equal to the following fraction: S evaluated at 1 over 15 and 0, and then you take the difference of the function values, divided by the difference of the two t coordinates, 1 over 15 minus 0. Now, in the denominator, that's just 1 over 15. But in the numerator, the things that we're subtracting are the following. S of 0, the position at the origin at the start is at 0 because we defined S of t to be the measurement of the position from the first patrol car. So at time 0, our truck is in front of the first patrol car, so the location is 0. And then S of 1 over 15, that will be the location of the truck after 4 minutes, but then that location is where the second patrol car is, which is 5 miles away from the first patrol car. So the numerator is 5 minus 0. Then when you divide by 1 over 15 minus 0, straightforward calculation provides us with 75. Well, what then is this good for? Remember, the derivative s prime of c is the velocity at time c. And so that means that there is this particular time c during those 4 minutes where the velocity was 75 miles per hour. Now clearly, this is way beyond the speed limit of 60 miles per hour. Alright, so that's the solution to the problem. Of course, we made these assumptions here, and in case you were wondering why you had to make this conversion, it's for reasons of consistency. The miles per hour rates are in terms of hours, so that would be inconsistent with the 4 minutes. So either you convert these two rates into miles per second, but then you would have to make two conversions. It was easier to just make one conversion, 4 minutes in terms of hours, 1 over 15.